Okay, so now we are going to talk about simplifying radicals. So in the previous lesson, we did a couple of examples using the Pythagorean theorem. One example, we didn't need to simplify the radical. The radical was already in the simplest form. And the other one, we had to break it down a little bit to simplify the radical. So I just wanted to do this quick lessons to talk about simplifying radicals all the way through in their complete forms. So we're going to work on 3 examples. The first 2 examples are going to take advantage of, that's a 9. The first 2 examples are going to take advantage of knowing your perfect squares. Your perfect squares, numbers that when you take the square root of them, there's no decimal remainder. So your 4s, your 9s, your 16s, and your 25s, things of that nature, right? So first, let's take a look at example number 1, the square root of 72. So if you know your perfect squares and you're pretty confident in them, you can ask yourself, what is the highest perfect square that goes into 72, right? And most of the time we'll start at 4 or 9 or things of that nature. And yes, those are perfect squares. However, they are not the highest perfect squares. Okay? So you want to try to get a remainder when you divide the number, in this case 72, by a perfect square that has no perfect square as part of the remainder. So here's what I mean by that. So 72, for example. 72, well, the highest perfect square that goes into 72 would be 36, because 36 times 2 is 72, and conversely 72 divided by 36 is 2. So I can rewrite the square root of 72 as the square root of 36 times the square root of 2. Okay? So we know that 36 is a perfect square, and we know that the square root of 36 is 2. So the square root of 36, the square root of 36 is not 2. The square root of 36 is 6. So the square root of 36 is 6. So I can rewrite this square root of 36 as 6. Now, 2 is not a perfect square. And if I took the square root of it, I'd get a decimal answer. So I don't need to simplify it any further. So this is written as 6 times the square root of 2. And that's my final answer. Okay? So next, the square root of 192. So this one, once again, you need to know your perfect squares, otherwise you do a bunch of guesswork. And not that there's anything wrong with that, but it just, saves you a little bit of time if you know your perfect squares. So 192, the highest perfect square that goes into it, that goes into 192, is 64. Okay? So 192 divided by 64 gives me 3. So I can rewrite 192, or the square root of 192, as the square root of 64 times the square root of 3. Okay. And then, just how I did on this first example, I do the same thing. Well, the square root of 64, which is a perfect square, can be written as 8. And 3 here, prime number, if I take the square root of it, I get a decimal answer. So I'm just going to write 8 times the square root of 3, or 8 square root of 3. Okay? So that's how you simplify radicals if you know your perfect squares. Now take a look at this last example. Pretty big number, kind of hard to figure out, well, man, what's the highest perfect square that goes into it? And things of that nature. And if you're not confident or comfortable with your perfect squares, there is a way to do this. Okay? So the first thing I like to do is I'm going to write the 342 and like an upside down division symbol. Okay? So then, instead of the largest number, I say, well, what is the smallest number that goes into 342? What's the smallest factor of 342? And naturally, everybody says 2. So 342 divided by 2 gives me 171. So I take this 2 right here, and it's 171 is the remainder. And I continue on with my box. Now, all the numbers out here are square roots, because remember, we're still simplifying radicals, so there are square roots out here. Okay? So next I have to ask myself, well, what is the smallest number that goes into 171? Well, I can't do 171 divided by 2 because that would give me a decimal answer, 85.5. However, if I take 171, let's try 3. If I divide it by 3, so that becomes the square root of 3, I get a remainder of 57. Okay? So I don't need to know my perfect squares, and I'm already getting there. So 57. Well, let's see. What's 57 divided by 3? That's the smallest number I can think of. 19. So I can divide this 57 by 3 and get a 19 in the remainder. Okay? So is there a number that goes into 19? Well, let's see. 19 divided by 3 is a decimal answer. Let's try 7. Nope. So 19 actually is a prime number, so I can't simplify it anymore, or I can't divide anything else by it other than 1 and itself, which is what I'm going to do. So 19 divided by 19, well, that's the square root of 19. And what's my remainder? 1. And once I get to this point, I am done with this work. Okay? So what I need to do now is multiply all these radicals together, because everything in between here I am multiplying. And if you have any matching radicals, in this case 2 square roots of 3's, I can rewrite those as just 3's. Okay? So the square root of 3 times the square root of 3, oh, that's 9. Okay? Or that's the square root of 9, which is 3. Okay? So then I can combine the 19 and the 2 as square roots. So 19 times 2 is 38. So because they don't match, it is rewritten as the square root of 38. So 38, not 36. It's 38. Okay. So 3 times 38. Okay. So my final answer here is 3 times the square root of 38. Okay. And this takes advantage of, I don't necessarily know my perfect squares, and there's no perfect square that goes into 38 evenly without creating a decimal answer, right? So if you know your perfect squares, you could have done, oh, well, you know, I could have just divided 342 divided by 9, got the square root of 9 times the square root of 38, and gotten the exact same answer. But you can do this method for this example and this example as well. But this example just kind of breaks down how to find the simplest form of the radical without having to know your perfect squares. I do suggest you learn your perfect squares because it will make your life a little bit easier. But regardless, this is how you simplify radicals